Hey friends, welcome to the YouTube channel. In this video, we will see how to use an op-amp as the integrator. Now, in the earlier videos of an op-amp, we have seen how to use an op-amp as a summing amplifier and the differential amplifier. And in this configuration, so far we have used resistors with this op-amp. Now suppose, if we use the reactive element like inductor or capacitor along with this op-amp, then we can use this op-amp as an integrator or differentiator. In this video, we will see how to use this op-amp as an integrator by using the resistors and capacitors along with this op-amp. First of all, just look at this inverting op-amp configuration. And in this configuration, the feedback resistor RF is connected between the output terminal and the inverting input terminal. Now suppose, if we replace this feedback resistor with a capacitor, then the same circuit can be used as an integrator. Let us understand how this circuit will act as an integrator. In this circuit, let's assume that the current that is entering into this resistor R is, let's say, RIN. And the current that is going out of this node is, let's say, current IC, that is the current which is flowing through this capacitor C. And as this capacitor is connected in the feedback, so let's say this capacitor is CF. So, now, here, because of the feedback, this node will act as a virtual ground. So, at this node, the potential will be equal to 0. So, let's apply KCL at this node. If we apply KCL, then we can write it as IN that is equal to IC, which is the current that is flowing through this capacitor CF. Now, this current IN will be equal to VIN minus 0 divided by this resistor R, and that will be equal to this current IC. Now, if you know about the capacitor current, then the current IC can be given by the expression C times D, VC/dt, where VC is the voltage across this capacitor. Now, we have already seen this expression in the earlier video of transient analysis, right? But if you don't know about it, then let us quickly go through it. The charge across the capacitor can be given by the expression C times the voltage across the capacitor. So, if you take the derivative of this expression, then we will get the rate of change of charge. That is equal to current, that is equal to C times D, VC/dt. And here we are assuming that the capacitance is not changing with time. In this way, we got this expression. Now let's use this expression and put this value in this expression. If you put this value, then we will get VIN divided by R, which is equal to CF times D VC/dt, where VC is the voltage across this capacitor. So, we can write this expression as CF times D/dt, 0 volt, which will come out as VIN divided by R, that is equal to CF times D volt/dt. So, if we rearrange this expression, then we can write it as D volt/dt, that is equal to 1/RCF, VIN, and if we take integration on both sides, then we will get the output voltage as volt, that is equal to -1 divided by RCF times integration of the input voltage. And here we are assuming that we have no output voltage at this terminal before we have started the integration. Suppose we have initial voltage at this terminal before the integration, then we have one more term that is equal to volt, 0 plus. That is the initial output voltage before we have started the integration. This is the expression of the output voltage in terms of the input voltage. As you can see here, the output voltage is the integration of the input voltage. And here this term RCF represents the integration time of this integrator. Using this circuit, we can integrate any input signal. Suppose if you apply 1 volt of DC signal at the input, then at the output you will get this signal. As you can see, initially, the output voltage will increase in a negative direction, and at a certain point, the output voltage will get saturated. Because the output voltage cannot go beyond the saturation voltage, right? Now, here the rate at which this output voltage reaches the saturation point depends upon the value of this R and feedback capacitor CF. By changing the value of this R and CF, we can change the slope of this output signal. Similarly, if we apply the sinusoidal signal at the input, that is sine weight, then at the output, we will get a cosine signal. That is cosine weight. And likewise, if you apply the square wave at the input, then at the output you will get a triangular wave. Now, here the amplitude of the output signal depends upon the value of R and CF. And that will be get cleared to you when we will take a few examples based on this integrator circuit. Now so far we have seen this simple integrator circuit and we understood that using this circuit we can integrate any input signal. But in real life, if you use this integrator, then you may not get the desired output which you should get using the theoretical calculations. Let's understand the limitations of this simple integrator circuit, and let's also see how we can overcome these limitations. To understand that, let's write the output voltage in terms of the impedance of this capacitor and the resistor. So, now we know that the reactance of this capacitor can be given by the expression 1 divided by WC right, which is equal to 1 divided by 2 pi times Fc. We can write the output voltage VOT as Xc divided by the R times the input voltage Vin. Or we can say that the gain of this op-amp will be equal to Xc divided by R, that is equal to minus 1 divided by 2 pi times RCF. From this expression, you can see that at 0 Hz or at very low frequencies, the gain of the op-amp will be very high, and ideally, it will be equal to infinite. But practically the gain of the op-amp will be limited by the open loop gain of the op-amp. At 0 Hz, the gain of the op-amp will be equal to the open loop gain of the op-amp. Because at 0 Hz, or at DC level, this capacitor will act as an open circuit. And because of that, the input voltage will be get amplified by the open loop gain of the op-amp. The output will always get saturated. And as the frequency increases, the reactance of this capacitor will reduce. And because of that, the output voltage will also reduce. If you see the frequency response of a simple integrator, then it will look like this. At 0 Hz or at DC level, the gain of this integrator will be equal to the open loop gain of this op-amp. And this open loop gain used to be in the range of 10 to the power 5 to the 10 to the power 6. In decibel, we can say that it is equal to 100 decibels. And as the frequency increases, the gain will reduce. Now, suppose if you are using this op-amp at, let's say, this frequency, then you should not face the problem of the very high gain of this integrator. But even if you use the op-amp at this frequency, then also it is quite possible that your output will get either distorted or saturated. Now, the reason for this saturation or distortion is the input offset voltage of the op-amp. Because in real-life scenarios, the op-amps which we are using are not ideal. And every practical op-amp has some sort of input offset voltage. Even though this input offset voltage is a few millivolts. But still, it can saturate the output of this op-amp. Let's say a few millivolts of input offset voltage is present at this terminal. This input offset voltage will be get integrated by this capacitor. And eventually, the output of this op-amp will go towards saturation. In this way, even though you are operating at a higher frequency, but because of this input offset voltage, your output may be getting saturated. We can avoid this problem by introducing one more resistor in the feedback in parallel with this capacitor. In this way, by introducing one more resistor, in parallel with this capacitor, we can avoid the problem of saturation of the output voltage. Because now if you see at low frequencies, this capacitor will act as an open circuit. At voltage or at low frequencies, the gain which is being seen by this op-amp will be equal to RF/R1. Even though few millivolts of input offset voltage is present at the input terminal, it will only get multiplied by this factor. In this way, we can avoid the problem of saturation. If you see any practical integrator, you will find this feedback resistor in parallel with this capacitor. Moreover, that if you see any practical integrator, you will also find the resistor, which is being connected at the non-inverting terminal. Basically, this resistor is connected to avoid the effect of input bias currents. We will see more about this input offset voltage and the input bias currents in a separate video. Now, because of this feedback resistor RF, if you see the frequency response of any practical integrator, then it will look like this. As you can see here, at low frequencies, the gain which is being seen by the op-amp will be equal to constant, and this equal to RF divided by R1. And as we go beyond certain frequencies, then you will see the reduction in the output. And if you see the response of this integrator, it is very similar to the response of low pass filter. And in fact, it will act as a low-pass filter. Let us say here the 3 decibels frequency or the cutoff frequency of this integrator is FL. Now if you apply any input signal, which is having frequency lesser than this cutoff frequency FL, then op-amp will act as inverting op-amp and it will provide the constant gain of RF divided by R1. To use this op-amp as integrator, input signal should have frequency larger than this cutoff frequency FL. And this cutoff frequency FL can be given by the expression 1 divided by 2 pi times RF CF. As you go beyond this cutoff frequency FL, you will see a reduction in the output voltage. And at one particular frequency, the gain of this integrator will be equal to 0 decibel. Let's say this frequency is 0 decibel frequency of, let's say, F0. This F0 can be represented as 1 divided by 2 pi times RCF. So, proper integration of the input signal, the input frequency should be larger than this cutoff frequency FL. And for proper integration, this signal frequency should be at least 10 times this cutoff frequency FL. To integrate any input signal properly, the input signal frequency should be in between this cutoff frequency FL and 0 decibel frequency F0. Well, practically you can also go beyond this 0 decibel frequency, but if you go beyond this 0 decibel frequency, then you will see the attenuation in the output signal. So, for the proper integration of any input signal, it should lie between this cutoff frequency FL and F0. Now let's take some examples based on this integrator so that the concept will be clear to you. Here we have a practical integrator circuit, and in this circuit, we have been asked to the low frequency limit for this integration. Here the value of this feedback capacitor is 10 NF and the value of this feedback resistor is 100 K, while the value of this resistor R is 1 kilo ohm. So, we know that the expression of this cutoff frequency FL is equal to 1 divided by 2 pi times RF CF. So, if we put the value of this RF and CF, then the value of cutoff frequency FL will come out as 159 Hz. For proper integration, the input signal frequency should be larger than this cutoff frequency FL. And for proper integration, it should be at least 10 times this cutoff frequency FL. So, in this way, based on your input signal range, you can design your integrator. So, now let's see the second example. In this example, the circuit is the same circuit that we have seen in the last example, but nowhere, the input signal is sinusoidal. And if you see it here, the frequency of the input signal is 5 kHz. Now, we have already seen that the cutoff frequency of this integrator is 159 Hz. And for proper integration, the signal frequency should be at least 10 times this cutoff frequency, which comes out as 1.59 kHz. Now, here if you see, the input frequency, it is 5 kHz. This signal will properly get integrated. Let's find the expression for the output voltage. We know that the output voltage VOT can be given by the expression -1 divided by RCF, multiplied by the integration VIN dt. Now, here the value of R is 1 kilo ohm and the value of CF is 10 NF. Let's put all the values into this expression. Now if you put all these values, and integrate this signal, then you will get 10 to the power 5, divide by 2 pi times 5000, multiplied by cos, 2 pi 5000 t, if you simplify it then you will get 3.18 cos, 2 pi 5000 t, this will be the output voltage VOT after the integration. As you can see here, the amplitude of the output voltage depends upon the value of R, CF, and input signal frequency. Now let's see one more example based on this integrator circuit. In this example the circuit is the same, but now the input signal has been changed from the sinusoidal signal to the square wave. And we need to find the output voltage at this end. Now, we know that whenever we apply any square wave to the integrator, the output voltage will be equal to a triangular wave. Let's find the amplitude of this triangular wave and let's also see whether this signal fulfills the criteria of our integration. If you see here, the time period of this square wave is equal to 100 microseconds. In frequency, if you say, the frequency is equal to 10 kHz. Now, for this circuit, we have already seen that the cutoff frequency FL is 159 Hz. And here the signal frequency is way beyond this cutoff frequency. It is ensured that the input signal will be properly get integrated. Now let's find the amplitude of this integrated signal. So, to find the output voltage, let's divide this square wave into the different segments. We can say that for 0 to 50 microseconds, our input signal is 2 volts. While from 50 to 100 microseconds, our input signal is minus 2 volts. We can integrate individual segments, and later on, we can add individual responses. For the first segment, our output voltage VO1 will be equal to minus 1 divided by R times CF, integration V1T dt, which will be equal to minus 10 to the power 5, integration 0 to 50 microsecond, 2 dt. That will be equal to minus 10 to the power 5, into 50 microseconds, into 2. If you simplify it, then you will get the output voltage as minus 10 volts. We can say that for 0 to 50 microseconds, the voltage swing is minus 10 volts. Or we can say that the output signal is going from 5 volts to minus 5 volts. Similarly, if we integrate this particular segment, then we will get the same 10V voltage swing but in opposite direction. In this way, if you see the output will vary from 5 volts to minus 5 volts. And as the input signal frequency is far beyond this cutoff frequency, you will see the proper integration of the input signal. Before I end up this video, here is the last example for you to exercise. This is the circuit of the integrator, and to this circuit, we have applied this input signal. You need to find the integrated output signal. So, let me just give you the hint about the shape of the output waveform. So, as you can see here, we are applying input for 1 millisecond. So, for this particular 1 millisecond, we will see the output will look like this. And from 1 millisecond to 4 milliseconds, as there is no input, so the output will remain as it is. And once again, from 4 milliseconds to 5 milliseconds, as we are applying the input, we will see the output will look like this. If you see the output waveform will look like this. But just calculate the value of this output voltage and do let me know that value in the comment section below. I hope in this video, you understood how to design the integrator using the op-amp. So, if you have any questions or suggestions, do let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.